March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues here have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So
wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
Into the equations that we want to use to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code, you're saying it is computer code.
It's not even just is computer code, it's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we can say are supersymmetric.
Okay. Time to go home, I think. I mean, where are we going to go? So are you saying we are all just, there's some entity that programs?
That they dictate that there are certain things that are actually strings of ones and zeros. That's just digital data. But it's not just random ones and zeros. As I mentioned earlier, let me talk about something that you probably do every day, but I don't know if you're a computer scientist or not. Most of us sit at our...
Sounds that kind of fluency.
Okay, well, most of us sit at our computer screens and we type on the keyboards, and we then send these, if we're using a browser, we're sending strings of ones and zeros elsewhere. But on the other hand, in the transmission process, there's always some fluctuations. So 0 that you type here because of static in line might be read as a 1 at the other end and vice versa. And so in fact, when you sit and type on the keyboard, your computer's doing something behind your back. Namely, it throws in a bunch of extra ones and zeros, and these things are called error correcting codes, so that the computer at the other end can look at the whole collection of what you typed plus what was sent and figure out if there were bits that were being flipped back and forth. And that's how you get accurate transmission of digital data. Among the codes that are used for this purpose are a special class of codes that are called block linear self-dual error correcting codes. They were first, in fact, the Shannon extended checksum code is an example of one of these things. These are the codes that we find buried in the equations. Not just any code, but these self-dual error correcting block codes. It's quite remarkable for anyone that I've talked to. We have no idea what these things are doing there.
Any literature out?
I'm sorry?
I got to ask you something. Your discoveries of these sort of error correcting code within the laws of physics themselves at the depths that you're researching them what I wonder is, we live in the age of IT, of information technology, so we all have a certain fluency. So it's in our brains to think that way at some level. Could it be that, you know how the saying goes, if you're a hammer, then all your problems look like nails, and you solve them by hitting them. If now we are in an IT revolution, and you're finding IT solutions to your problems, maybe it's just the fad of the moment, and you're forcing a solution that is either not real or there's a better one awaiting in a revolution that has yet to occur.
Sure. So the last time I was here, I actually misspoke. I used the name of Shannon when I meant Hamming code instead. So first, let me correct that for this wonderful audience.
Error correction in action.
That's right. Exactly. Error correction in action. Absolutely. But in our work, it's first of all, we don't know that it's the physics of our universe.
There is a large experiment underway that Lisa knows a lot about in Geneva because she has written papers about possible outcomes in these observations.
Lisa, are you flying to Geneva tomorrow?
I am, but not for that.
Not for that, okay.
So the Large Hadron Collider is going to explore more of the structure of the universe. So first, the mathematics that I have done will only become physics or relevant to nature when the LHC or some other observational device says the idea of supersymmetry is correct. Then it will kick in. So that's a big if. There are lots of physicists who don't believe the universe will be supersymmetric, in which case all I've done is an interesting mathematical fairy tale.
So supersymmetric proposes a whole other regime of particles that are counterparts to the particles we've come to know and love?
Correct.
Okay, and they're yet to be discovered, but they could be describing a whole other parallel reality awaiting our discovery.
But even that, I mean, I just want to clarify, we may or may not find evidence at the Large Hadron Collider, which is what's being discussed, but that doesn't even mean that supersymmetry doesn't exist. It means that we can't find the evidence at the scales that we can prove.